Okay, so in today's lecture, we're going to introduce a algorithm called k-nearest neighbors and show how this algorithm can be used to write a computer program to provide recommendations for a user. So let me just write the title down. So k nearest neighbors and recommender systems. Okay. So this algorithm, k-nearest neighbors, relies on the notion of distance between feature vectors. And from last time, well, in the last lecture, say you recall, that the norm of the difference between vectors x and y is the distance between vectors x and y. So the distance between vectors x and y. Right. So this is a useful notion, like an incredibly useful notion, because when dealing with data, the data that you receive, that you are dealing with, oftentimes measures quantities that are of the same type, right? You're looking at a vector where the first component is the price of rent, the second component is the number of bedrooms, so forth and so on, right? So when you have a collection of feature vectors, the vectors that are more similar will tend to be clustered around each other, right? And with this idea, we can then look at the distance between a given vector and all of the other feature vectors around it, and the vectors that are closest to it are somehow just like the vector that we're looking at. So maybe we could recommend whatever labels correspond to those feature vectors to a user. And it's a little jumbled the way I described it, admittedly, but I think if we have a concrete example, you'll get what I'm saying. So here's the scenario, and I'll pick up on the example from the last video about the movie recommendations. So actually, let me first describe the algorithm and then look at the application of the algorithm. So I'll go ahead and write it out. So k-nearest neighbors. Okay, so that's the name of the algorithm, and as input, you have a collection of data vectors, maybe say D. So collection of feature vectors. Together with the labels of each vector. And then also k, which is just some natural number. So natural number is a counting number like 1, 2, 3, 4, so forth and so on. So it's a natural number. Okay, and then what is it? Output. The output of this algorithm is going to be the k closest oh, wait a minute, I almost forgot. One more thing to input here. So a collection of feature vectors together with the labels of each vector, k, a natural number, and then a vector maybe v, a vector not in D, and then your output will be the k closest vectors in D to V. Okay, so that's more or less the idea that is set up behind the algorithm. We have an input, an output, and now how do we achieve this? Well, there's varying different ways to do this, but basically what you want is you want to say scroll through each vector in D and calculate its distance to V using this norm. And once you have all those distances, the k closest of them are the ones you want to output from the algorithm. Okay, so basically, you can order the vectors in D as follows. So, so what do you want? So we want a collection of k vectors, say, I don't know, D prime instead of D, so that x minus y, all in norm, is less than or equal to the norm of x minus, oh no, I should use b here. So v minus y is less than or equal to, in norm, v minus x in norm for all x in d prime and y in not in d prime. Okay. So the idea is that we want to find a collection of vectors that are the k closest. It's hard for me to write it out because it's such a simple idea, right? It's just input, output the k closest things that satisfy this two norm. Okay. So why would this make sense? Or what is like an example of implementing this algorithm? Well, as we talked about before, we can have a collection D of data that have entries, right? So we have this collection D of data of movies and then their IMDb rating, whether or not they're a horror film, whether or not they're a drama, whether or not they're a documentary. We can have this collection of data. So And a lot of times data will come as a CSV file. And I'm going to run out of room here. This is going to keep on going. But for a given name, I don't know, just whatever, A, B, C, D, E, so forth and so on. We have some numerical rating, I don't know, 1.9, 7.2, 8.3, 4.4, 6.0. And then we have maybe this is a horror, this is not, horror, horror, not documentary, no, no, yes, so forth and so on. In this data, we can kind of transform into a collection of vectors together with their labels. So we have the label, which would be the name, and then this row corresponds to the feature vector for that name. So, comma, 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 dot, dot, comma, 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 dot, dot, just like we did last time. And each of these features, feature vectors, lives somewhere in, if there's n features, they each live somewhere in n-dimensional space. And provided that none of the entries are too far away from each other numerically, they're all roughly close to each other, which they more or less are if these IMDb ratings are more than 10. Then somewhere in space, they're going to have distances between each other, right? And if you input, say, this vector, and you'd like to look at the k nearest neighbors to that vector, you're going to get a recommendation for another movie to watch, okay? Or several. If you choose k to be 5, then you would have 5 movies that would be closest to it that you could then recommend to the user. And this is what's called a recommender system. Now, one thing to be careful about, though, and this is not a topic for this course, this is a topic for a machine learning course or a more data science centered course, is that as the dimensionality of these feature vectors grow, the feature space becomes very empty. And if you look at the distances between these vectors and you're looking at this really large dimensional space, it's going to be skewed. And this is something called the Curse of Dimensionality. And this is a problem that in the future you will address. For now, we're just going to use this data and kind of look at the k nearest neighbors and ignore that. But just know that it exists, that when you have high dimensional vectors and you're looking at the distances between them, they can be very far apart. And similar vectors can be very far apart. And this is where things like dimensionality reduction, or feature selection come into play, where you want to look at the most important features. Well, how do you find those, right? But again, that's for a machine learning course. This is a linear algebra, calculus-based course, math course. So we're just going to take this as is and program k nearest neighbors to make a recommendation for k nearest movies for a given input movie. Okay, so let me go ahead and pull up my screen.
You said the problem was called recursive dimensionality, is that right?
No, the curse of dimensionality.
Oh, gotcha. Okay.
Okay, so there is this movie data set. Let me just that I've posted on Blackboard under the data sets folder. And it's in my current working directory, so I'm just going to open up a Python Jupyter notebook. And I'll use pandas to read in the CSV file. And I'll use NumPy to do my standard vector operations. Okay, and then let's go ahead and read the data in. The data CSV, I'll say is equal to pandas.read CSV. And I think I called this movies recommendation data.csv. I think that's what it's called. Let me double check. Movies recommendation data CSV. Okay, so just read that in. Okay, so if we're going to find the k nearest neighbors of the data, we have quite a few things to do first. So first off, let's look at the CSV file. Let's just do that. So each column here, so we have the IMDb ratings. Is it a biography? Is it a drama, thriller, comedy, crime, so forth and so on. And then we have the names here. So to access the columns of this pandas data frame, we can just do the name of the data frame dot, actually, I'll use df. That's probably a little bit standard, more standard than CSV. So df. Okay, so we can do dot movie name to get the movie name column from that data frame. Okay. And we can do dot biography to do the biography column. So I'm just going to use, I don't know, let's just use like the IMDb rating, and then let's use, is it a biography? Is it a drama, thriller? And that's it. Let's just use those four features. And the way that we can do that is say, okay, I'm going to make what am I going to do? So we need to somehow associate the labels with the feature vectors in a convenient way to make our recommender system. So the way that I'm going to do that is I'm going to make a dictionary. So data dictionary is going to be, okay, so how can I do this? Okay. There's a few different ways to do this. So let me just do something real fast by saying D is equal to, oh, I know what to do. This is probably sloppy, but we'll get over it. X for X in zip data df dot movie name, comma, data df dot IMDb rating, data dot df, no, not dot, sorry, data df dot biography, data df dot drama. And by the way, in Python, you can make this look a little bit nicer by doing this. And then we wanted a thriller, right? Okay. So what this did, oh, here. So what this did is it made a list of tuples. Okay. So actually, what I would like to do is maybe put this as a list of lists instead of tuples. Zip makes lists by, zip makes tuples which are immutable, and I don't really like that. So what I'm going to do is I'm going to put all of these into a list. 1, 2, 3. So how many entries? 0, 1, 2, 3, 4. Okay, so now these are all lists. Okay, and now that I have this list, I'm going to now make the dictionary that I wanted. Okay, so how can I do that? Well, I'm going to do this. I'm going to say data dictionary is equal to x0, comma, and now, so x0 is going to be this. It's going to be, so, or x in D, but now I need to give it the feature vector associated with that label. Okay, so the way that I'm going to do that is I'm going to say mp.array x from 1 to the end. So now here's the 1 entry, and it's going to go all the way to the end, and then it's going to convert that to a NumPy array. And at that moment, each movie name is going to be associated with a NumPy array. So let's see what it looks like. Okay. So that's nice. So now we should easily be able to calculate the distance between a given movie and another movie. So for example, well, in order to do that, we need a function that's going to make calculate the distance. So I can just make that real fast. Norm between vectors x and y. And we're going to just return x minus y at x minus y. Oh, and we need to take the square root of that. np dot square root of that. So this is the square root of x minus y transpose, x minus y inner product x minus y, and that is the 2 norm, right? The square root of inner product is the 2 norm. Okay, so now we can just make sure that that norm works by saying, okay, what is the norm? Oh, maybe that norm distance. Sorry. Distance is what I wanted. So let's make sure this works. Distance between data dict of maybe the imitation game and data dict of ex machina. So, yep. Looks like we got an error here, so let's see. Oh, wait a minute. That doesn't look right. What is the type of this? Oh no. Shape. I might have made a silly mistake. I'm just checking it right now. right? They're not the same size, and that's because, oh, that I was when you convert lists to NumPy arrays, one way of doing it is to pass it just as a single list. I was passing it a list of a list, and that's why it was wrong there. So now this will work. So the distance between these two things, these two movies, is 1.445. So we can calculate the distance between two movies now. Okay, so now that we can do that, we can definitely calculate the distance between a given movie and all of the other movies, now that we can do it between two of them. So I think we can just finish it off now. So def k nearest neighbors. So we're going to pass it some dictionary D, and we're going to pass it some K. Okay, so we need to calculate the distance, and a given movie. Okay. I'll call this movie dictionary. I like to give the inputs to my functions different names than what I've named them outside of the function. It's just a preference of mine. I just want the names to be descriptive. So I want a movie dictionary. It has the names associated with the feature vectors. I want an input movie to test on, to recommend on, and I want I want the K closest movies to my given movie. So in order to do that, there's a few different ways to do that. I'm going to choose to make a list of this information. So maybe distance list equals empty list. And then for X in movie dictionary, I want to say distance list dot append, and then inside of that I'm going to put inside there a tuple. No, I'll put inside there a list that has the movie's name, and then in the next entry I'm going to put the distance between X and the movie in question. So to do that, we use movie dict X, comma, movie dict the movie in question. So that's the name of the movie here, and then the next entry is that the distance between the movies and the movie in question. And then I'm going to sort this list by the second entry. So you can sort lists by doing distance list dot sort. And now we're going to give it a special key because this is a list of lists. How do you sort that? Well, we're going to say that we're going to sort that by key. So the key is like the numeric value for which we're sorting. And we're going to pass it a function called lambda. It takes in X and returns X1. So I know many of you probably haven't seen this before, but let me just like make a new cell down here just so you can see it. So if L was equal to A10 R 3 T 6, and that's your list L. You can sort this by doing L dot sort and saying what's the key that you're going to sort it by, and then pass it this lambda function. Lambda is a one-line function, and it takes, you have your input there, and then colon, and then what do you want it to return? It's going to return the one entry. So we're going to sort this by the one entry. And then if we look at L now, 3, 6, 10, it's been sorted. So that's what we're doing here. Distance list has the movie names, and then the second entry is the distance to our movie in question. So I'm just sorting that by the distances. And then I'm just going to return the first K entries. So return distance list, and we're going to go from 0 to, not 0, 1 to K plus 1, because the 0 entry is going to be the movie itself, because that movie is going to be in there. So you don't want to look at that one. Okay, so let's see if this works. And just get rid of all this trash down here. All right. And let's pass it our data dictionary. And then what movie do we want to look at? Maybe what are the movies? Let me just look at some quick ones. I don't know. I guess the Avengers, maybe. Oh, Terminator. I like the Terminator. All right, so let's see what happens if we pass that in there, and then let's look at like the top 5 results. Okay. Avatar, the Avengers, Thor, Black Panther, Spirited Away. So those are the top 5 recommended movies based off of those features, right? And we used just the first 4. Let's see if it changes if we add a few of these. Like, I guess we can add all of them. Doesn't matter to me. So let's go ahead and add all of them, or almost all of them, with the exception of the last one. So now I'm just gonna update my data. Comedy. I just copy and pasted, that's why it looks that way. Crime. Data df mystery, and then history. Data df history. Okay, so just why it's doing that. Typically when it's doing that, it means there's an error somewhere. And I need to make that again. Let's see if this distance changed, because I added all those extra columns or extra features to see if the distance changed. Yeah, it's basically the same. So then this doesn't have to change. So let's look at now. That's new. That wasn't there before. Maybe let's look at the imitation game. Let's put that in there. I'm just curious. And not that I know too much about these movies, but it doesn't seem like it's doing terrible, right? It seems like it's all right, let's try Forrest Gump. Okay. That one's different than these like action movies. Let's see what happens when we put that one in there. And I know Forrest Gump pretty well, so okay, I could see how Good Will Hunting would be there, right? So what's the key takeaway here? It's basically that this distance function that you can use on vectors can tell you a lot about data and where data is located in Rn. Now, there are tons of caveats to this, as I mentioned, but in a very naive way, already, we barely have been working with vectors in any advanced way. We're just learning about distance and the inner product, and we're already able to take in data and make useful predictions. Okay. So I guess I'll stop the recording there. Okay, any questions about k nearest neighbors?
What was the last column used for, the label column?
What do you mean?
In the movie data set, there was a last column where every entry was a 0 label.
I don't know what that is.
Okay,
It's
just not relevant.
yeah, I just know that I'm pretty sure it's all zeros.
Gotcha.
We can look at the norm of it real fast and see. So data df. Capital L, capital L. The norm will tell us if it's all zeros. If it's all zeros, the norm will be 0. That was one of the properties that we discussed last time. So I'm just going to call this little thing x, and then np dot square root of x inner product x. And let's see what it is. Yep, it's all zeros.
Gotcha. Okay.
Also, if you are looking around at code, you might also see x dot I don't know. There's another way of doing inner product. I always use the @ symbol just because it's the simplest. Okay. Yeah.
Sorry, I also wanted to ask, I don't know how like familiar you are with like the Netflix prize or the Netflix competition.
I'm a little familiar with it.
Do you know how they improved that algorithm? Like whether they were just choosing different variables to analyze, or did they do a completely different machine learning approach? Like, were they doing this algorithm, but just like picking and choosing the different aspects of the movies?
Oh, they were doing something different than this. This there's an algorithm that it's called PageRank that I'm pretty sure was used, but then also they do a lot of dimensionality reduction things as well. And modifying the data beforehand. So it's probably the case that some of you have wondered why we've looked at some of these like linear or affine functions applied to vectors. All of these functions that you see me write on the board that can be applied to vectors, if you see something applied to a vector, that means it can be applied to data. So, like maybe dividing a vector by a scalar, or subtracting off of a vector with some operation, like all of these things will modify the data to possibly make it more useful for the machine learning algorithms that you'll be doing at some point.
I was just about to ask, like, what is a useful application for this inner product data besides looking at like movies the way you did it? Like, what would be an actual application of this, like for data that we would get?
Well, it makes it a lot easier to, like for example, when I calculated the distance, I didn't have to write out a function that was specific to 2-dimensional, 3-dimensional, 4-dimensional vectors, right? Like the distance is the inner product. That's it. And you need to know distance between data all the time. So that's like kind of what I was writing out. So without the inner product, you don't know the distance. That's a super important application of it, because most things in data science require knowing distance between vectors. Also, we haven't gotten to it yet, but we will tomorrow. Where theta is the angle between x and y. So the sine of x times y, the sine of x inner product y, so that's always positive, that's always positive. The product can be negative or positive. Well, if it's negative, you know something about the angle between the two vectors. If it's positive, you know something about the angle between two vectors. And a lot of machine learning algorithms deal with modifying your vectors to change angles to make better predictions. And we won't get into too many details of that, but that's like another application. Is it, if you imagine the vectors in space, the inner product between those vectors will tell you the angle between them.
So I haven't taken the machine learning class yet, but will it mainly like focus on different ways to manipulate vectors in our like to optimize our program?
Well, even outside of machine learning, pretty much everything is a vector. Like everything in data science is a collection of entries. Data is a vector. There is no data that's like just a single number. All data consists of multiple things, which are vectors, because typically there's order in them. So every bit of like not just machine learning, but just vectors, as I mentioned at the very the first day of class, pretty much, they're the most important thing, mathematical object to a data scientist. And the reason is data comes in the form of vectors. And understanding, for example, the distance between vectors, the inner product between vectors telling you the angle, like just being able to use these tools gives you the ability to perform data analysis. And I think that maybe there's some YouTube videos I can or a YouTube playlist I can put on Blackboard that might give you a little bit more insight as to the ideas behind the vectors more. But yeah, it's they're really the heart of everything that you'll end up doing.
Yeah, I'll take those YouTube videos. And then last question, that Lambda function, because I've seen it before, but I don't think I've fully understood it. It's really just like a getter function for our list.
The lambda functions on their own are just one line. They're called anonymous functions. So, for example, I can do suppose I want to just do x plus 1 or something. So just like return x plus 1. So that's one way to write a function. Another way would be to say f equals lambda. I think this is the syntax. I never do it this way. think I can do this, something like that. No, this doesn't look right. Yeah. Is it just F? Oh, there's two X's there. And then, okay,
Concatenation, like adding the previous one with this function, because I would need that one. Like, I know there's like a specific function for it in Python, but not in R, to where we can take like the previous day and subtract it, just like I don't think it's called a concatenation. Like,
well, that would be something completely else. This is Lambda is just a way to write a quick function to do whatever you want. Like, so see how I could define F this way, just like normally,
yeah.
and then I do F of 10 is 11, but I can also define G as the same exact function this way. It's the same thing. This is your input, and then this is your output.
Okay.
So like, if I wanted to say like, maybe take in X, and if X was like a list, return like the third entry, and then like, I don't know, A, B, C, D, it returns the third entry. It's just a way of writing. It's a way to write functions in one line, but you should never do this the way that I just did it. Not like that. The only time that you should ever use lambda functions are inside of sorting arguments. So key equals to some function and you want to do it real quick, just throw in that. Typically, you would avoid that and just write functions fully out. Like another way that I could have done this function right here, another way I could have sorted this, I could have just done this takes in that, and then this is going to return the one entry. And then instead of doing a lambda function, I could have said key equals get one's entry like that, and that would work as well. It's just a quick way of doing it. That's the only time the lambdas really get used. Okay.
Thank you.
Okay, so I guess that will be it for today. I'm gonna post this recording on YouTube, and then I'll also post a vectors or linear algebra playlist from 3 Blue 1 Brown that you should watch. And then also don't forget that homeworks 1 and 2 are up. Okay.